Let's discuss about data processing instructions of ARM Cortex-M4. These instructions are used to manipulate the data within the CPU registers. The first data processing instruction is the move instruction. This instruction is used to move the data to the CPU registers. The general format of this instruction is move, destination register, and operand 2. So operand 2 is a flexible operand that can be some other CPU register or a constant value. So the move instruction copies the value of operand 2 to the destination register. By default, move instruction moves 16-bit of the value to the lower half word of the register. If you want to move 16-bit value to the top half word, you need to use MOVT instruction. For example, in this line of code, this constant value will be shifted to the lower half word of register R6. And the next instruction will move the content of R6 to register R7. The third instruction, we are using MOVT, so this constant value will be moved to the upper half word of register R7. Let's see how move instruction executes and affect the CPU registers on actual microcontroller board. For that, you need to connect your TIVA C Series LaunchPad with your computer and start debug session. Select your test file and the line that you want to debug. Hit run to cursor line. Now you can step one by one through these instructions. The first line moves this constant value to register R6. You can see by default register R6 is blank, it contains nothing. Now if you step one line, you can see this constant value has been moved to the register R6, and the next line moves the content of register R6 to the R7. If we run this line of code, you can see the register 7 is also updated with the same value. In both lines, you can observe the 16-bit value has been stored to the lower half word of the register. Because all these registers are 32-bit wide and the values we are moving are 16-bit wide. So the third instruction, move TR7, is moving this constant value to the register 7's upper half word. Let's execute this instruction, and you observe the constant value has been updated to the upper half word and the lower half word does not change. This data processing instruction adds the two operands and stores its result in the destination register. If the destination register is not specified, then it will store the result in the first operand. Let's see how this add data processing instruction work. First of all, we need to move these two constant values to register R5 and R6. As you can see, register R5 and R6 has been updated. Now this instruction will add register R5 and R6 and stores the result back in register R7. Let's see. So you can see register R7 has been updated with the sum of R5 and R6. In the next line, since we have not specified the destination register, therefore register R6 and R5 will be added and result will be stored back in register R6. So in this instruction, when I execute it, you can observe the value of register R6 changes. This data processing instruction perform subtraction without carry. This is the general syntax of this instruction, and this instruction subtracts the operand 2 from the R value and stores the result in destination register. This destination register is optional, and if it is not specified, the result will be stored into the first operand. So let's see how this instruction executes and affects the register on actual microcontroller. First of all, we need to move these two constant values to register R5 and R6. And you can observe register 5 and 6 has been updated with these values. Now this instruction will perform subtraction. It will subtract the content of register R6 from R5 and stores the result in register R7. Let's execute this line of code, and you can observe the register R7 has been updated with the difference of these two registers. In the next line, we have not specified the destination register, therefore the result will be stored in the register R5, and you can see the register R5 has been updated with the value of the result. This assembly language instruction will multiply its two operands and return least significant 32-bit of the result. It will store the result in the destination register, and if this register is not specified, it will store the result in the first operand. Let's see how this instruction affects the actual registers. First of all, we will move these two constant values to register R5 and R6, and you can see those registers changing. The next line of code will multiply register content of register R5 with content of register R6 and stores the result back to register 7, and you can observe how register R7 changes. In the next line, we have not specified the destination register, so register 5 and register 6 content will be multiplied and result will be stored back to register R5. So keep an eye on this register R5. The product is placed on register R5. And instruction. This data processing instruction performs logical AND operation. It performs bitwise AND operation between its two operands and stores the result back in destination register. AND operator can be used to turn off particular bits in our register. Consider this register value, and we want to turn off bit 7 and bit 3. For that, we need to make a mask which will act as second operand of the instruction such that its bit 7 and bit 3 is 0 while all the remaining bits are 1. Now if you take logical AND of register and mask value, you will find that all the other values of the register remains unchanged, but the bit 3 and bit 7 turned off. Let's verify this example on actual microcontroller registers. First of all, we need to move this value to register R5 and mask value to register R6. Now the next instruction will take a bitwise AND between the content of register R5 and R6 and will place the result back into register R7. So keep an eye on register R7. Next instruction is also performing the same operation as the above line, and it is updating register 8. This logical data processing instruction performs logical OR operation. It performs bitwise OR operation between its two operand and stores the result back to destination register. This OR instruction is used to turn on particular bits in a register. Let's look at this example. In this example, we want to turn on bit 4 and bit 1 of the register. So we need to make a mask such that all the remaining bits are 0 and those bits will be 1 that we need to turn on. Now if we take the logical OR of these two values, we will get this result, and you can observe in the result that the corresponding bits are turned on and all the remaining bits of the registers are the same. Let's observe it on the actual microcontroller registers. First of all, we need to move these two constant values to the registers. Okay, so this instruction will take a logical OR of register R5 and R6 and put the result back into register R7. And similarly, the next line of code is also doing the same, but the result is saved to the register R8 now this time. This logical data processing instruction performs logical exclusive OR. It takes two operands and performs their bitwise exclusive OR and stores the result back to the destination register. This exclusive OR operator is used to toggle particular bits in a register value. Consider the same example. Now we want to toggle bit 7 and bit 4 of the register value. For that, we create a mask such that only those bits will be 1 that we want to toggle and the remaining bits value remains the 0. So when we take the exclusive OR of these two values, we will get the result. And in the result, you can observe the bit 7 has toggled from 1 to 0 and bit 4 has toggled from 0 to 1, while all the remaining bits remains the same. We can also observe the same on the actual microcontroller registers. Register R5 and R6 has been loaded with the values. Now this instruction will take exclusive OR of content of R5 and R6 and put the result back into register R7. And similarly, the next instruction also performs the same operation and stores the result back into register 8. Let's talk about some of the data processing instructions that operate by manipulating bits of the registers. The first instruction that we will discuss is the logical shift right instruction. This instruction shifts the bits towards the right side of the register. This illustration shows this logical shift right by 3 places. As you can see, the bit 31 is shifted to bit 28 and bit 30 is shifted to bit 27 and so on. Also, the 3 vacated bit positions we have inserted zeros. This is the syntax of this instruction. First of all, we use mnemonic LSR, then we specify the destination register, and then we need to provide the first operand, and the second operand can be a register or that can be a constant shift value. The important thing to note about the logical shift right instruction is that it provides the unsigned value of a register divided by a variable power of 2. In this example instruction, the content of register R2 is logically shifted right by a constant value of 2. The value in register R0 is 1024. It is a decimal value, and when we do logical shift right, you can see every bit is shifted towards right by 2 places, and the new value becomes 256, which is equivalent to dividing the original value by 2 raised to power 2 where 2 is the constant shift. Let's see how this instruction execute on an actual microcontroller available on TIVA C Series LaunchPad. Okay, first of all, let's move the value in register R5. You can notice the value moved to register R5 is in a hex value, which is hex 400. That value is equivalent to 1024 in decimal. Okay, when we executed this instruction, you can see the register R7 is loaded with the hex value 100. So the value in register R5 was 400, hex 400, and register R7 contains 100. So it is justifying that the logical shift right instruction has divided the registered value by the 2 raised to power of the constant shift. Arithmetic shift right instruction is similar to logical shift right instruction, but the only difference is it works with signed value. Therefore, when it shifts the bits towards the right, instead of inserting zeros, it inserts ones into vacated bit positions. As you can see in this example, we have a signed value 1024 stored in register R0. As you know, signed values are stored in the memory in its 2's complement. So when this instruction is executed, it has an effect of dividing the signed value by 4. Let's see how this instruction is executed on actual microcontroller. In this line of code, you can observe that we are not using move instruction because move can only shift maximum of 1 byte of signed data. So this instruction is subtracting this constant value from the existing value of the register R5. Since the register R5 contains 0, and when we subtract this constant value from 0, we will get negative of this value. So this was the trick to move a big signed value to a general purpose register. You can observe its hex equivalent has been moved to register R5. So moving on, when this instruction is executed, you can observe the register R7 has been updated with its result. You may notice the content of R7 is equivalent to minus hex 100 or minus 256 in decimal. Logical shift left instruction is the opposite of logical shift right instruction, because in this instruction the bits are shifted towards left instead of right, and zeros are inserted into the vacated bit positions. The logical shift left instruction provides the value of a register multiplied by a variable power of 2. The variable is the constant shift that we provide in this instruction. For example, in this instruction, the content of R0 will be multiplied by 2 raised to power 7. The 7 is the constant shift that we are giving in this instruction. Let's execute this instruction on actual microcontroller board. Let's move some constant values to register R5 and R6. And when this instruction is executed, you can see the constant value 7 will be multiplied by 2 raised to power 7, which is the value of shift, and we will get this value. Its hex equivalent is 380. So you can see register R7 and R8 has been updated with this hex value. Rotate right instruction provides the value for register rotated by a value. The bits that are rotated off the right end are inserted into the vacant position on the left. It have the same syntax as other shift instructions. So let's execute an example on actual microcontroller. First of all, let's move some constant values in register R5 and R6. The next line of code will execute rotate right instruction. And you can observe register 8 and register 7 has been loaded with this value, which is equivalent of rotating the entire register value by 2 bits towards right. Rotate right extended instruction provides the value of content of a register shifted right just 1 bit. As you can see, every bit is shifted towards right by a single place, and the least significant bit is shifted towards the carry flag, and the carry flag is shifted into the most significant bit, 31. Let's see this in microvision Keil. Let's move this constant value to register R5. When we execute this instruction, you can observe the updated value in register R6. So that was a short introduction to some of the data processing instructions available for ARM Cortex M4 microcontrollers. If you have any questions, you can ask it in comments.